in this video we're going to build a simple list data structure from scratch. So what are going to be different and what am I going to implement in here is that this won't be like any other list. I'm going to imitate the list functions and the features available for it in C++, and I will be making the operations that you can do with a list more intuitive. Like for example, if you add a plus operator to add to list, it will be added, to be precise, it will be concatenated, joined end to end, and yeah. So like that, I'm going to implement several other features into this, and without wasting any time, let's get started. How we are doing. So in this video, we are going to make a simple list data structure from scratch, and this time it is going to be a little different. Like I have planned to implement all the features which are available in Python in C++. So what am I going to do is a little bit creative, like using operators. You may argue that it is already present in the standard template library as well, but like doing things from scratch changes everything and gives you a bit clarity, okay, isn't it? So actually recently I have been studying about operator overloading, so I thought of why couldn't I put that into use and make C++ more intuitive. For example, you can add to list, you can subtract a list from one another. So like that kind of features I'm planning to implement in it, and the standard data structure will also be included in the same. So without wasting any time, let's get started. Guys, these are the implementation which I'll be doing in this. You might be wondering what is this class buffer, slots, and all these functions and all. So let me explain it later. Just for now, I will share a link in the comment section. You just click on it, you'll be redirected to a LinkedIn page where I would have written all the stuff about what is a buffer. Basically, it's a memory allocator, but in this case, the slots will be continuous. So because of that, the execution time will be reduced. The complexity will be very, very less. To be precise, this one is a dynamic heap memory allocation tool, which helps us get the memory slots in a way that it is cache friendly or cache friendly. So so these are the functions which we are going to implement and invoke. So this is a constructor, obviously. We'll be adding elements. For adding elements, insert, push friend, push back. For removing element, all this. And for searching, you would know the functionalities. And size and memory availability, this capacity is a new one. Okay, so this capacity just fetches the data about the availability of slots. So basically this buffer, what it is going to do is, it is going to create 10 slots at max. So in each these 10 slots, there will be 16 MB of contiguous memory will be available. So that memory will be used to allocate the elements which are pushed into this list. So we can't keep pushing elements into this just like that, isn't it? Because once the 16 MB memory limit is exceeded, the next chunk of memory will be used for memory allocation purposes. So we want to know like up to how much we can fill our data in, right? So in order to get that info, I have introduced the capacity function, which is basically going to give the information about how much the memory is available, or how much elements I can insert in this list such that it remains cache friendly, okay, or cache friendly. So that's it. And okay, I forgot to include a deconstructor, which is a must. So we'll be doing a lot of memory allocation stuff and dynamic memory allocation. I need not say all those things. You guys would probably know how hectic it is. So if we just forget to free a pointer, it will cause a memory leak. So developing a data structure is not important, but managing the memory is important. So which is non-negotiable. Let me include that as well. Actually, this deconstructor is going to help us free up the RAM and handle all those dynamic allocation when the list is expired, or you can say the function of list is no more required. This is going to help us organize memory and free up the space, and this is going to fetch memory for us. And so I haven't filled any pointers or variables here because I still didn't have any idea about what naming should I give or how do I even proceed. So I'll be writing a simple blueprint of it textually, and I'll be just proceeding in that order. So we are going to start implementing these functions. Writing these functions one by one, and after completing this, we'll be looking into the operator sections, so how we can modify it and those things and all. And with all the required function and stating it here, so I'm going to proceed with the blueprint for how to build the structure. So before that, I want to tell you something like how I'm going to proceed with things. I'm going to notify each and every element that is being pushed into this list. So why exactly I'm doing this is because my arena allocator works in a specific way such that the feature of the given list gets interrupted because of that. So let me give you a glimpse of how my arena allocator works. Basically, what it does is when I request for RAM, it just allocates memory or gives me hands me over the memory continuously. For example, right now I'm storing an integer 7, let's say. It is giving me an address 0x001, let's say. Now next I want to store a character. I ask for some memory, let's say 1 byte. Then it gives me memory address which is immediately next to that integer, stored next to that integer. So when this happens, the space wastage is reduced completely. And at the same time, what happens is when I try to push list in a randomized way, when I have more than one list, for example, I have list 1 and list 2. In list 1 I'm pushing number 5, and in list 2 I'm pushing number 10. So when I do this, when I push number 5 will be stored at the first address, and number 10 will be stored immediately next to it. So what happens is navigating through the elements of a given list will become difficult and inefficient. So in order to avoid that, notifying each and every elements which are being pushed into a given list, we can navigate through that easily. So it's basically like two nodes are being connected with a string. So here string is nothing but the reference or pointer which we are going to use, and this pointer will be referenced by the previous node and the current node as well. So in order to navigate back and forth, and the nodes are going to be the classes which I'm going to construct right now. So why we are doing this is because the CPU works much faster when there is lot of data that will be processed are in a continuous array of memory addresses. So what I mean is that when a CPU tries to read a data from RAM, it is really slow. So what the CPU does is that it just copies the data, whatever data, either it may be a single integer or a garbage value. It just reads a memory of 1 kilobyte and stores it into its own private memory space. So by doing that, it need not go to the RAM and again fetch the data and come back. So it can just see whatever data which is present continuously. Okay. So when this happens, the reading the data becomes much more efficient. Okay. So in order to induce this, we are trying to create an arena allocator with just request for a large chunk of memory, and in that large chunk of memory we are going to store whatever data we want to store in that. So dynamically, to be precise, what we want to store in that, so such that the RAM, like the CPU, can fetch the entire chunk of memory and store it in its own private memory space. Okay, because of this, data reading becomes efficient and the implementation of a given data structure becomes much faster. And now let me just start with this pushback because that is easier much. So what I'm going to do right now is I'm going to push back in the sense okay, there are two variables which are included here. So one is head node and another one is end node. So what does that mean probably, and the node looks somewhat like this. Yeah, and this one is template class, like a class described using the template. So the node has these three information stored in it. One is what is the next node, and another one is what is the previous node, and the value what it stores. So classes are basically objects which can store its own features or attributes. So now let us write the implementation for pushback. So since pushback means a node will be added to the tail of the list. Okay, so first what we will do is, if head node is equal to a null pointer, what we will do is we will assign the head node, that is we will create a head node okay. So query node. Okay, good. Before that I need to declare the object. Okay, so that needs to be done. Same template, let me do. The name is buffer. Let me call it arena. So it's just sounding somewhat fancy. Now yeah, what happens here is if the head node is not a null pointer, then head node will be assigned the pointer node. We will create a new node and make it as the head node here. Else we are going to create a node. Let us call it current node, and we are going to query for the memory space for it. Okay, now this is a pointer to a new memory location in the arena. Now what needs to be done is that this node should have reference to the previous node as well as the upcoming new node, okay, if possible. So when I push back, I need to look before, not after, okay, because I'm just attaching new tail to it, isn't it? So I'm attaching new tail to it. So now what we are going to do is we are going to take the end node. Okay, so end node and consider its previous node. Okay, sorry, next node. In its next node, we are going to write this current node. Okay, now the previous node knows what the next node or where the next node is present. Now we need to make the current node as the end node. Now end node is equal to current node. Yeah, we are done with this. Yay. So we forgot one thing. So when head node is not present, we are going to create a new node. Okay, so while creating that implies it doesn't have a tail as well, so we need to make the tail node, sorry, it's end node. So end node as head node. Okay, so yeah, now we are done. So initially, so okay, let me draw a simple figure of it. Now initially a node is there. Node 1. Okay, so okay, now when this if statement, when the head node is not, first of all the list is just declared. In that case, what happens is first head node is being generated. So after it gets generated, it also becomes the end node as well as the head node. Now when I try to create another node, okay, when I try to create another node, that is when I try to push element from the back, attach a new tail, what happens is I'm creating a new node. Okay, still it is not being attached to it. Okay, I'm just creating a new node. Let it be somewhere far away, node 2. Then I get this address. Now what I will do is I will go to this node and I will say that I will tell to this node that your next node will be having this memory address. So now this node 2 is getting connected to node head, and what I'm doing next, end node is equal to current node. Okay, so this node becomes the end node. So what I'm telling is that the head node knows what is its next node going to be, what is its tail is going to be. So as soon as I create another node, I'm going to implement the this line of code to tell this list that this node 2 is going to be present right now as a tail, as an end node. That's it. So yeah, that's it. Pushback is complete. And yeah, we forgot one other thing, that is we need to include the value. So let us say value is being passed and I don't know the data type of it. So okay, let me erase this. Okay, so now I have this head node dot value is equal to value. Okay, that's it. So we are done. Now the same goes for this as well, but in this case current node value. Okay, now let us go to the push front function. The same thing is going to happen there. Okay, same thing is going to happen there, but this time it is not going to be head node, it is going to be end node. So what we are going to do is that, okay, push front, end node. Okay, it's kind of confusing right now. Push front in the sense I will be adding a new head. So when I add a new head, I'll be looking whether the head node is present or not. Okay, this also will be head node. Okay, so when the head node is null pointer, what happens is the head node becomes this, and this end node also becomes the same. Okay, if not, current node will be fetching the memory address for the same. And now the end node has previous node is equal to current node. Now head node is equal to current node values. So yeah, so what happens here is, first of all, this push front or push back, both will check whether the any element is present or not. So how it is going to check that is by saying whether the head node exists at all. So if the head node doesn't even exist, it creates a new head node. And it will say that this head node is the end node and then store the value in it. Yeah, fine, that's it. Now if the head node is already present, then what will happen is you will create a temporary node and we will just inform to that head node, or the here it should be so it's not end node but it's head node. Okay, so yeah, as I said, we are informing the head node that your previous node is going to be the current node, and we are saying that after saying that to the current, like the apparent head node, we are saying that whatever node we are created right now is going to be the head node after this. So now current node becomes the head node and current node stores the value. So okay, so let us store the value. Yup, so we did it. Okay, now since we have wrote the implementation for adding a node that is pushing a value, either push back or push front, now it's over. Now we will be moving to pop front and back. Okay, pop front and back clear. Okay, fine, clear, find, reverse. Okay, so pop front. So pop front is nothing but reversing what we have done here. what we have done here, we have created a node and made it as a head node. Okay, but in pop friend we will be doing the exact opposite of it. We will be destroying the node which is the head node. Okay, for that what we will be doing is, if head node is equal to null pointer, then std cout, there is no head element present. Okay, so yep, so we have added a safety feature in it. There is no element present. Else, if head node is there, what we are going to do right now is cout. Okay, std cout. Okay, std cout. We need to return a value, right? Or not? Yeah, so it is going to return a value. So return head node. Okay, it is not a good idea to do that. We need to create a temporary node. Let us say node star is equal to temporary is equal to head node. Yup, so now we are safe. Head node value. Okay, so head node value will be returned, and yep, it's time to destroy the head node. Destroying in the sense we are going to rewrite the head node. That is like reassign the head node. We are saying now after popping the front node, the current head node won't be present. So instead of destroying it, I'm just reassigning it here. Why? Because there is a very particular reason for it. Why? Because that's how my arena allocator works. Since it is like half complete, updating it later would be precise, because it involved a lot of pointer arithmetics and stuff. So like it literally fried my brain. So okay, let us proceed. Head node. From the head node we are going to okay, so no, head node is equal to temporary node, which is head node obviously, from the next node. Okay, so now this becomes the head node, and so we need to intentionally do memory leaking here, because the arena allocator doesn't handle that. yeah, now the operator functions and everything is done. Operator overloading is handled properly, and everything is working fine. And I'm sorry that I could not show you much of it while creating all this, but I'll make sure that you get to see all the things which I have done here by posting our GitHub repo link in the comment section below. And I know what, it took me 3 painful hours to debug all of these things, and obviously, yeah, I referred to internet, and yeah, I was able to learn like a lot of things of it. So I was able to learn what is a cache line and what it has to offer, and what is the constant keyword does to a given variable, and how the compiler optimizes it for our sake. So yeah, a lot of things was able to appear to my eyes, which I had been ignoring for a very long time. So, and here is the demonstration of all the functions which I have created, to be precise, methods which I have created in this class. So let us do a quick run here. Okay, let me explain. So there are two lists. In list 1, I'm just pushing the elements 9, 8, and 7, 3. Okay, and in list 2, I'm just pushing number 8. So I'm reversing the list 1, and in the list 1, I'm inserting the number 11 at 0th index, and I'm making list 1 is equal to list 2, and in list 1, I'm removing 3. So now here the first output is being demonstrated. Now the size of list 1 would be 1. Why? Because I have did list 1 is equal to list 2. List 2 has only one element, and that too it is 8. So find 8. It is at the 0th index. Yeah, good. From list 1, I'll be removing 11. Okay, there is no such element. Okay, there is no such element, so it can't be removed. So it silently fails. And again, we try to pop the element which is present in list 1, that is pop friend. So yeah, we get 8, and again pop back 8. So list 1 dot clear. Now if we see the size of it, it is 0. I'm asking whether this list is empty or not. Yes, it is empty. What the hell, like, there is a bug. There is a bug. So as you can see that I have only pushed a single element into this list 2, that is number 8. And what I did was I did list 1 is equal to list 2. That means now currently list 1 is having only the element 8, and I'm trying to remove 3 from the list 1, so it is not there. So if you look at the standard layout, the size is 1. Yeah, it is accurate. Now when it tries to find the number 8, its index is at 0. Okay, so size is 1, index is at index of 8 is 0, and if you try to remove 11, okay, there is no element is present, so nothing is outputted. So when we do list 1 dot pop friend, 8 is coming. Okay, fine. But when we do std cout list 1 dot pop back, still we are getting 8. How is that possible? Because we have only one single element in that, right? So after that, everything is working fine. So there is a problem with pop friend and pop back, or like there is something wrong with this assignment of operator. So either of that should be the case, because when this will happen is that actually, as I said before, this arena allocator doesn't deallocate the memory location, so the node still exists there at the memory space. So when this happens is that when the end node is not a null pointer. Okay, when the end node is not a null pointer. Okay, when we look at this case pop friend, what it says is whether the head node is present or not, whether it is a null pointer or not. Okay, if it is a null pointer, it will return there is no element present, and if it is not a null pointer, it will give out the element back. But when we look at pop back, it also does the same. But when we have a single element, for example, let us say list 1 dot pop friend, list 1 dot pop back. Okay, for example, let us say we are doing pop friend. That means we are setting head node to be a null pointer. Okay, when we do list 1 dot pop back, we are setting the current node's next node as null pointer. Okay, current nodes, current end nodes, the node which is present just before end node, we are setting the next node of that is going to be a null pointer. We are going to say that. But when we do that, we are not explicitly knowing that whether it is a single node or a it is a single node or it has more than one node. So in the case of single node, when we use pop friend, what happens is that we are saying to the list that the current head node is being removed. So that means since it has only single element, you consider head node to be the null pointer, but we didn't mention that end since it has only one element, the end node is not going to be present as well. So we need to solve this problem. So I think I have explained it in like I just stretched it a lot, so you people would have been bored. So let me show you what happens actually in this pop friend and pop back. So in pop friend, it checks whether the current node is null pointer. So next what we are doing, we are like it just checks the current node's next node, and it just changes the head node. That's it. Okay, it just changes the head node, the pointer to the head node, not the end node. But when it has only one node, the given operation is it kind of creates nuisance. That is, it leaves out the possibility that the end node could also be a null pointer. Okay? The end node should also be set to null pointer. Okay, so how are we going to resolve this? So I have added this another conditional statement in that, which states that if the number of nodes is equal to 1, then what you do is, okay, so this is unnecessary. What you do is that you set the head node to be a null pointer, and the end node to be the null pointer as well, and reduce the total number of nodes which is present. And what you're going to do is that this temporary, like I have stored this temporary, I have stored the head node's memory address and the temporary pointer. So using that pointer, just fetch the value. That's what I'm saying here. And I did the same. Now let's check whether this is working or not. Hope it works. Okay. What it says before it ends. Okay. Expected a. What did I do? Okay. Yeah, my bad. Syntactical mistake. Okay. What about this? Yeah. So let's cross our fingers. It will definitely work. Yeah, it worked. Yay. So 108, there is no element present, -10. Yeah, I have perfectly handled this as well. So now it's in 100% working condition. I can say that safely because like I just like after writing this conditional statements, I just gave this to Gemini and asked it whether will there be any crash. I mean, like, not crash, is there any bug? And it turned out that I made a very like I didn't even make any mistake. Actually, it was quite surprising because usually whenever I send any code or project which I do to like Gemini to learn somewhat new things, because that's how I learn. I will just give Gemini to I will give the code to given AI, and I will ask it whether how can I improve, how a senior architect would do things, how he would handle, so such that I will be able to learn new things. That's how I learned this const variable and its use, and how it helps us optimize the optimize the given program. So actually, it was quite surprising that I didn't make any structural mistakes, and every other function was working right for now. So yeah, that's it. I'm just done with all this list data structure. So let me close this vlog right here. So if you have any suggestions, or if you think this could have been done in this particular way, or the structure could have been a little better, or you should have been doing this in this particular way so things would be efficient, if you think any of it, please just comment in the comment section below. I'll be more than happy to look at it, and I just want to learn. And if you want to learn, you can also ask me some questions about it, so we can share our thoughts. And yeah, that's it. Stay tuned for the next video. In the next video, I'm going to talk about optimizing this arena allocator and how it works as well. So stay tuned.